Good morning to everybody. Good morning or good afternoon, depending upon where you are in the world. Hope you're having a good day. Welcome to the Meeting Modern HMI Challenges event. Thank you for joining. I am going to start on time because although some people are still joining, I'm going to start on time because we have a lot to get through in the hour. So I would like to welcome everybody that's joined on behalf of Core AVI, DDCI, and PRESAGIS. This webinar, which is put on jointly by 3 partners that are working together to try and help solve your problems. Today, we're going to try and talk to you about taking advantage of new developments in devices, tools, and software in order to build modern HMI systems. We're not talking about cell phones or web-based stuff. The market I've tried to describe here: airborne systems, ground-based UAV control systems, industrial, military vehicles. And throughout the introduction, I'm going to refer to people involved in that as crew. Okay? So that's what I mean by that. We're aiming to talk for about an hour. But at least some of us will be available after the end of the hour if you have questions. And we're going to address all of your questions at the end of the presentations. I mentioned earlier to those who were on a little bit earlier to please use the chat window to talk to us. I put the icon, this icon. You should be able to find that in your WebEx connection, and that will allow you to chat with us. And all the panelists that are here will see your messages. Also, one other request. When you leave the meeting, a short survey will appear on in your browser. Please take the time to complete that. It will help us in improving these in the future and making sure that we've satisfied what you need. Thank you very much. As I said, this webinar is being put on jointly by 3 partner companies: Core AVI, DDCI, and PRESAGIS. Core AVI is a leading supplier of real-time safety-critical graphics drivers, hardware IP, and embedded graphics processors. Over the last 20 years or more, Core AVI has been deployed in more than 130 programs in more than 20 countries around the world. DDCI provides D178C certifiable software for safety-critical avionics, including the DIOS real-time operating system. DIOS is a time and space partitioned RTOS that's certified to D178 level A and includes the innovative SafeMC technology for multi-core processors. And PRESAGIS is a leading provider of tools for HMI software development and deploying those HMIs to embedded or airborne hardware. PRESAGIS has supplied cockpit display systems software tools since 1985, and the company also provides solutions for ARINC 661 and D178 certification. So the agenda today, we're going to first of all have a quick introduction to the overall topic that we're talking about. Then there'll be a presentation from PRESAGIS, from Core AVI, and from DDCI, and then we'll take your questions. So first of all, to introduce what the topic of what we're going to talk about. One of the main challenges that we see facing HMI developers overall is workload. That's a very broad statement, but by workload, I mean 2 main aspects. The workload of the crew in the vehicles and systems that we're developing, and the workload of the system developers themselves, how they put these systems together and get them certified and get them out. So the pilots, drivers, supervisors, commanders, wingmen, ground controllers, and so on, they're all facing increasing complexity in the domain in which they work. Things are happening more rapidly. In military vehicles, rapid attacks and things, responses to those have to be done very quickly. All of that information needs to be interpreted, had to be interpreted rapidly, especially when you're under critical circumstances, when something's going wrong in the aircraft and you don't know exactly what it is, or when you're under attack in a military aircraft. So all the displays that we provide overall need to inform a shared understanding and to support clear decision-making for the safety of that crew. Likewise, in the lab, when we're developing these systems, there's fierce competition to win deals in these markets. And so it's important for us to get our products to market faster. Device obsolescence is driving technology revamps, so people want to update their equipment in the field. And also, as we develop new techniques, new algorithms, new capabilities, there's a demand to deploy those new technologies to the vehicles more rapidly. So for these developers, we need to improve their efficiency in creating designs, in validating those designs and deploying them to the various vehicles. There's been enormous developments in the last few years in kind of display technology, much of it driven by handheld devices like phones and tablets. But now it's common in these vehicles to see large area displays, head-up displays, helmet-mounted displays, and so on. And we're also seeing techniques for sensor fusion and other sophisticated algorithms being used and deployed into vehicles to help people. The methods of interacting with systems, how you so bezel keys are an old type of way of doing things, but now we see multi-touch and gestures being used. We see systems that track eye movements. We can talk to our systems and so on. All of those are part of the way that we interact with systems and need to be taken into account in our human-machine interfaces. Lower down in the hierarchy, behind the scenes, as it were, the GPU capability has advanced dramatically in the last 5 years. Those GPUs can now be used for computation as well as rendering graphics. You have multiple cores in GPUs now that mean that we can partition graphics applications. And partitioning in the CPU is now a common way of dealing with multiple design assurance levels on a single CPU, but those CPUs now have multiple cores. So how we access those multiple cores and release the power that gives us in systems in a safe way. That's a very important technique that we'll be talking about here. So back in the lab, as I said, the rapid pace of competition is forcing us to get our products to market faster. We need to look at faster design and development measurements, techniques. Things like rapid prototyping, validation, all those have to be accelerated. We need to get sign-off from our customers. We need to get certification. We want to be able to integrate with legacy systems that we don't want to have to rebuild. And we want to be able to reuse things that we've already developed, models and technology that's already been created, because it doesn't make sense to rebuild it. So, management's demand is get it right first time, right? And that's an admirable goal, but it's not always possible. But we do it as much as we can. Also in this world, we're surrounded by standards, right? Standards for certification, making sure that the systems that we deploy in various vehicles is safe, These are airborne software standards that I've mentioned here. For graphics, there are again rapid developments in the standards that allow us to deploy things. We're using OpenGL SC2, which brings in shader support, and Vulkan, which is gives us the capability for multiple threads. ARINC 661 is a standard that's widely used. It enables you to separate what's in the cockpit from the actual vehicle, what's in the back of the plane. And now there's a new standard to go with that, part 2 of ARINC 661, which is changing the world again. In the US particularly, FACE has had some success in creating a market for portable applications that can be developed by one company, and the system specifiers can mix and match those to some extent. So today we're going to be thinking of a system architecture that will underlie the things that we're talking about. Basically, we have an embedded system. Into that system, we're going to put some applications. So PRESAGIS will be talking about developing applications using tools and deploying them to this embedded platform. That will allow us to actually display graphics that is relevant. We also want to have interaction that comes into here. So mouse and touch and various other techniques will come into that application. And there's also connections that we have to make to the rest of the system in the aircraft or the vehicle that brings information in that's actually going to be displayed. Core AVI, they're going to be talking about partitioning graphics applications to make use of the latest GPU technology to improve performance and so on. So their graphics driver, which provides a support to modern GPUs, which will improve the ability to draw the graphics at speed and achieve performance goals. DDCI, we'll be talking about the operating system that I mentioned earlier, DOS. And that system allows us to partition the application space so that we can actually have multiple graphics applications running. So now you see down here that another display has appeared, which is coming from the other graphics applications. We can have other applications running in this system in a safe way, different non-graphics applications, maybe a data processing application like this. And so that, through a board support package, gives us access to multi-core CPUs. So that's my introduction. Now, at this point, I'm going to hand over to Matt Jackson, who is with PRESAGIS. Matt has worked on embedded hardware systems for more than 20 years. Sorry, I'm having a small issue with WebEx here. Sorry about that. Matt has worked on embedded hardware and software development for more than 20 years, specializing in HMI systems and real-time graphic systems. He's been involved particularly in touch-based systems and in ARINC 661 programs. Been an active member of the 661 committee for the past 11 years. Thank you, Matt.
Apologise, had a technical issue there as well. It wouldn't allow me to unmute my microphone. So thank you very much for the introduction there. What I'm going to walk through now is just looking at some of the modern HMI needs and some of the steps and processes that we need to think about and when we're developing As Paul mentioned before, there's kind of almost like a technology menu now. Previously, it was you develop your own technology or you had what was there. Now there's actually a kind of huge selection. And some of the challenge in building a new modern HMI, you actually have to consider how do you approach that problem and what do you do. So today we have an increased number of sensors, communication and additional technology on the platform that we're working on. So be it land or in the air. And this is just generating data and huge amounts of it, which obviously leads to a problem of pilot workload or crew workload, as Paul mentioned before. And you're looking to try and minimize that and actually ensure that they carry on with what their task is at hand and not spend the whole time just looking at information. So historically, depending on the HMI philosophy and workload, this could require a lot of space within your system to actually try and display this. So an example, an HMI philosophy used to be everything was dials and gauges. It worked well, but that was pretty much the technology you had available to you. So if you had more data, put another dial in there, put another gauge. But you can see that in this particular case, as you work forward, you just run out of space. So obviously, depending on your philosophy, you've got to look at ways of how you present that data and actually present it in a way that isn't overloading the user. So the format of that information has to be effective and not overloaded. And you now become this issue where you have a mix of safety critical and kind of mission critical. I use the word mission critical to cover the description of flying an aircraft from Paris to New York, or I'm trying to actually do a military mission. I'm actually managing a whole lot of systems and an objective at the end. And the safety critical side is I've got to make sure I do this without crashing or causing a problem here. And as you can see, moving from a dial-based thing to a multifunction display to a large area display in this picture, you've got to consider the kind of needs and the process that you're working with. So this leads me on. So we've got ways of now presenting information, and traditionally with a glass cockpit we would work with a multifunction display like we're showing in the top right hand corner of the screen, with bezel keys, cursor controls, mouse track, joystick, keyboards, that type of thing. But as we move forward, and if we start saying, well, actually we need as much real estate within the kind of display area, and we move to a large area display, we move into the interesting kind of challenge of how do you control that. So hopefully this video is coming through. I know we've got some bandwidth issues here, but the ability to touch or use touch gestures or voice actually makes things a lot faster, and the ability to move around that screen, it gives you a lot more flexibility. So the idea of how you interact with the systems has changed over the years. Before you had physical controls, now you can move into virtual controls with touch and gestures, and they may or may not be suitable for the particular use. And in this example, this is a mock-up that we've put together of just showing gesture usage within a large area display. And it actually highlights some of the challenges that you hit doing there. So I think in this example, we can pinch and zoom on the map. Traditionally, you would have done that with a hand controller or with keys on the bezel. And actually, most new users, this is quite a natural thing, is just reach out for the screen. So we have these new user input methods which are efficient, but there may be a need for more than one type of user input. So traditionally you may have used a bezel key or you may have used a cursor control. There may be needs for more of these and a multimodal input type approach. So this leads me on to how do you actually use all of this technology? There is a menu now available. It doesn't mean it's suitable for a platform. Evaluating the idea whilst it's on the ground or in your lab, it's better than waiting and making that decision or discovering a problem later on. So I've got some examples here. In the top left-hand corner, this is actually a prototype of looking at how to do a new menuing system using touch. So I've got a little debug in there that's showing my finger pressing on the screen. You have to press and hold to actually bring up the menu, and you get some animations in there. Now, these sort of simplistic prototypes are very, very helpful when you're looking at displaying information and interacting with it in a new way. The idea of just having kind of a menu and a pull down menu bar like you have on your desktop is not necessarily suitable for for a crew working on a safety critical system. So these new sort of concepts are useful to prototype. So validating how you do that is useful. However, it may not be suitable for the platform. So this kind of concept of checking on the usage with the human, but also validating it in its environment that it's going to be used with. So I've got a small recording here of actually trying to use a swipe gesture during turbulence. And this was actually recorded on a civilian aircraft sitting right at the back of the plane, trying to show the difference, because for those of you used to a tablet, people often say, hey, I just swipe my tablet to change page or change the screen. And it often comes up in discussions when you're making these type of things for a safe system. However, in this particular case, I have the ability where I've actually recorded. Oh, it's jumped forward here. Okay. Here we've actually recorded what's happening with a finger as I try and touch the screen. And it's actually been set up in such a way to try and look at the variation and the movement of the finger. So you'll notice a cone here. And because of the turbulence, you'll actually see that I'm attempting to swipe to the right or up, and actually my finger is moving in quite a large space. Now, on a traditional tablet or a phone, you've got a very small tolerance because the device is in your hand and it's all stabilized with you. When you're looking at an airborne system, you can see in this particular case that the actual turbulence is causing a finger to move. So is it the wrong technology or the wrong user input to use when developing your display? Maybe, maybe not. Maybe it actually needs tuning for your actual platform and your usage. So in this particular case, it's very clear once we have some data, we can actually see that the tolerances stay within these bounds. And as long as we keep within that, you can effectively recognize it even within turbulence. So that's just considering the concept of looking at how you interact with the system. Obviously, the ability to look at all this data presents us challenges of how do we present that to the crew or the end user. And we'll talk about this more with the kind of use of GPUs and sensor fusion here. But again, an example here of data. This is looking at what you have to do with this sort of thing and considering what you have to prototype and present to a user. So if we have a scenario here with the real world, so I've got a nice city and some mountains in the background. This is what's going on in the real world. Now, computers don't see the real world. What a computer sensor would see is, here's an example of some IR sensor information that's come back into the platform. And you can see the heat information of that terrain and buildings and vehicles and so forth on there. Now, I have the possibility I could have LiDAR as well. So I could get a point cloud back, and if I have a very bad LiDAR, this is actually a simulation of a LiDAR system with a low density LiDAR quality in there. And actually you'll find in cars and things like that, their LiDAR scanning is actually not very good. It gets disrupted by moisture and other things. So you don't get a very detailed picture. On other types of LiDAR, you might get a much more detailed build-up of the actual physical terrain, but this is what the sensors and the computing platform see. But do you want to present that to your user? How useful is this? What's the objective of the information you're trying to give to the user? Really, when you bring those two together, when people talk about sensor fusion, showing something like this to a user is actually not very helpful. Hey, I've merged the camera, the infrared, and my LiDAR data. How useful is that to my user? Reality is that just gives a workload overload to the user. What you're looking for is the sort of thing that you want to present to the actual end user in the HMI. So this processing could traditionally be done with a separate computing board or something like that to give you that information. But with the advent of multi-core or multi-partition systems, we can actually use a single board and use the power of GPU processing to do compute to actually build up something that's useful to present back to the HMI. So in this particular case, we've used compute to say, actually, here is your flight plan within this area in a 2D representation, top-down view. And what we're looking to do is either minimize maybe noise, maybe an air taxi, and we're looking at minimizing the noise for a populated area. It could be routing information to say, actually, this has got high traffic density, avoid this area. But the idea is it's now presented in a much more user-friendly approach rather than just overlaying data on top of data on top of data. And the advent of being able to do this inside a GPU, where previously you need a lot of computing power, you've now got this available on the same platform you're doing your HMI. So it could be a 2D, or it could be 3D you're trying to present. So actually you're saying, here's your corridor that you're flying through, here's your waypoints, and this is the actual corridor you're flying. Now, useful thing when you're doing this type of prototyping is to actually recognize the problems that come with it. It looks fine here, but I only need to change the perspective, and you realize that the information it's given you is you're going to have to fly through the side of the mountain, which is not very appropriate. So actually prototyping these sort of issues and showing this in a prototyped world helps for the development and using all this information. So what we're looking here is trying to get early validation. So the idea we try and give and suggestion we make for a lot of these complex systems is the more prototyping you do up front, so design what you want and look at what the information is available and try it out. You don't have to try it out on real avionics hardware. You can try it out on a tablet. So here's an example of an Android tablet running the same display as you saw earlier. Trying it out, getting the validation with the users or your end customers, and then refining it and actually trying to refine that very quickly. And in this sort of workflow, you can do that very quickly because you haven't heavily invested. But moving forward is as you kind of refine this, the ability to take your designs and move them forward into a simulator becomes more valuable. The use of simulators, especially with the sensor overload, and all of this new information becomes more useful because actually you're trying to assess the workload. So here's an example of actually displays running with a very simple out the window visual, and you're trying to fly it and monitor, is this effective? Is the user trying to see things that are useful? If I've got a sensor system, so a LiDAR simulator, because the ability to do that, and we have tools that actually help with this with IR and LiDAR models, that you can actually do this and then prototype some of your data fusion in the situation that's more accurate. So obviously we're talking about improving the process here, and especially with the more data, An HMI model, especially if you use it with tools to generate code and resources, can improve your development efficiency. If you try to kind of build one of those simulators or one of those prototypes, you can do it many ways. What you're looking to do, though, is to try and minimize the re-expression. If you are using a model, try and minimize that re-expression through multiple kind of iterations. So, hey, marketing come along with a nice PowerPoint, someone codes it up in a bit of Java, throws it into a 3D model, and eventually it gets into some code that you're going to fly. The problem with re-expressing is it leads to errors and misunderstanding as you pass it along. The idea of using a model, it should allow you to minimize that. And it's one of the things that actually industry is trying to address. ARINC 661 Part 2 and also ARINC 661 try to address some of this reuse of a model as an open standard, and actually saying, try and use the same thing as you move through to minimize this problem and misunderstanding. The other kind of thing when you're looking for reuse is with a modern HMI, you're trying to reuse things because actually display items may be required on different hardware or different display sizes. These display items or hardware devices, you may be deploying on one platform using an ARM CPU, and tomorrow you're using Intel for another variant that you have within the systems you're delivering, but you don't want to have to rebuild your code. So being able to reuse something and take it, and especially with a model you can do this, you have that ability. Now, the other challenge and where reuse you need to think about is often you have to have multiple applications on the same screen space, and you need to partition that because of certification. You don't want to design a model for a very low level certified environment or develop code and then actually have to upgrade it to a high certification. If you can split your models up and bring them together, this actually helps. So here's an example of a wide area display. I've got lots of information on here. What we'll see is actually some of it is safety critical, some of it's just mission critical. And if you look at how you build your system, you can break it up, especially if you consider reuse. So obviously we've built up something here. There are challenges when you come to deploy this. So it's very rare to start from a clean sheet design. Typically, there is always some legacy application to integrate graphics or a system. Now, one of the things moving forward, and I know some of the colleagues here are going to present about this, is the ability, if you use multi-partitioning or multi-core within the operating system, you can take some of these older applications and integrate them with your HMI. ARINC 661 gives you one way of integrating. FACE is another way that talks about how you bring in legacy applications, sharing the actual screen space safely. Obviously, certification. If we try to hand code all of this, it would be a huge amount of work. And if we end up as a monolith, any updates or upgrades in the future would be a problem. So we have this challenge of there is an upgrade cycle that's being reduced and there's more features being added. The variants of being deployed, quite often people are asked to deploy an HMI to 3 or 4 different platforms now. So we have this challenge in place. And obviously the other issue we have as mentioning is different variants and these hardware platforms. Everyone talks about standards, and I've worked long enough to know that actually hardware is different, and as much as OpenGL was good, there are problems. You can make the same OpenGL command on a different chip and it actually looks different. So you need to be able to tune and match your hardware and when you're deploying it. So you need to look at how you manage those configurations and those platforms there. Now, a consistent HMI model through the development and with certification tools can actually support and reduce many of these tasks, which leads me on to an overall workflow. So this was the workflow I had on the prototyping. If we can take the same model and move that forward and take the same model with certification tools and put that into embedded hardware, we can actually save a lot of time and money and have the ability to reuse it across platforms and reuse it across systems. And on that note, I will wrap up and pass back to Paul.
Thank you very much, Matt, for that presentation. I'm now going to ask Lucas Friesek to talk. Lucas is from Core AVI. Let me just give him the control. So Lucas has been a software developer with Core AVI for 4 years and has recently transitioned into this role of FAE. He has extensive hands-on experience in developing embedded software systems that are deployable in DO 178C safety critical environments. So Lucas, you should be able to take the screen. Thank you.
Okay, thank you very much for that, Paul. So in my presentation, I'm going to focus on the challenges of HMI development that Core AVI sees from a graphics driver development company. So I'm going to talk about the challenges we see, HMI system requirements that fall down to the driver level, which lead to things such as combined graphics and compute support, compute and sensor fusion, support for multi-application systems taking advantage of a single GPU or multiple GPUs, and then the reuse of graphics software. If you could advance to the next slide, please. So the challenges we see from a graphics driver developer perspective is that customers want applications that are high performance and have little latency. So what I mean by that is that when there is an update to a sensor or there's new data coming in, that there's very little latency from when that data comes in to when the screen shows the update. Our customers want to use multiple high resolution displays. So, 4K on multiple displays, two or more displays, multiple applications sharing the same GPU. So there can be multiple applications that are executing on potentially different cores, sharing a single GPU, and they might also have different certification levels as well. And then the last challenge that we see is that customers want to use the GPU for more than just graphics. They also want to be able to do GPU processing or GPU-based compute processing. Next slide, please. So from our perspective, this gives us the following system requirements. The application wants to take advantage of all hardware on the system. So this could be all functionality that the GPU provides, as well as the multiple cores that exist on the CPU. The GPU needs to be both used for processing graphics and processing data with technology such as GPGPU. The GPU is going to be used for data processing, actually in the case of sensor fusion. So as was spoken about before, the GPU can be used to accelerate the combination of sensor data. The GPU needs to be able to take advantage of the multiple cores on the system to process and execute multiple applications at the same time. And lastly, our customers want to reuse existing software where possible. So there's lots of legacy code that exists, and our customers don't really want to rewrite applications that they know work and simply won't use. Next slide, please. So my first focus here is just going to be talking about combined graphics and compute. So this is the case of using the GPU for both graphics and compute at the same time. So traditionally, GPUs only provided operations for doing graphics-based computation, so drawing graphics primitives, texturing, doing graphical transformations. But as GPU technology has advanced, the GPUs are capable of much more complex operations. So on the right side of the screen, I have an example of a GPU being used for object tracking. So in this case, there's an image of a UAV flying, and the GPU is doing processing on the image, and at different stages, you see the processing operations it's doing. So the GPU is being used for contrast adjustment on real-time video, or doing edge detection on real-time video, and lastly, doing object tracking based on an area of interest on real-time video. So this is not a traditional graphics workload. This is something in the past that would be computed by the CPU, but now with the more programmable abilities of the GPU has been exposed, the GPU can be used to parallelize and accelerate these computations. Next slide, please. So one issue with combined graphics and compute is that legacy graphics APIs such as OpenGL SC don't expose as much of the programmability of the GPU. So in the case of OpenGL SC1, there is no programmable functionality of the GPU exposed. It's only the graphics capabilities. With OpenGL SC2, some programmable capabilities of the GPU are exposed. In this case, vertex and fragment shaders, so you can write programs that run on the GPU that act on a per vertex or per fragment pixel computation. So this is nice if you want to do more complex graphical operations, but it doesn't give you general purpose GPU compute. This is very specialized, custom graphics accelerated compute. Now, modern graphics APIs such as Vulkan and Vulkan Safety Critical expose the more programmable nature of the GPU and allow general purpose GPU compute applications to be written. So on the slide here, you can see an example of some GPU-based compute operations. So there's range filtering, edge detection, contrast adjustment, blur filtering, standard deviation, and median filtering. So these are all operations that assist with doing edge detection on an image or noise removal on an image or clarity adjustment on an image. So these are all GPU accelerated compute operations that are accessible through GPU compute-based shaders that wouldn't have been as easy to expose using just vertex and fragment shaders. Next slide, please. So the next topic I want to talk about is compute and sensor fusion. So as mentioned before, sensor fusion, the idea behind that is combining data from multiple sensors into a single, easy to parse representation. So just simply overlaying sensor data on top of each other isn't always easy for the operator, user, pilot, whoever to understand. And so the idea behind this is that we want to combine sensor data in a meaningful way so that we're giving the operator an easy to parse display of information. The traditional issue with sensor fusion is that for some types of sensors that provide data in point clouds, images, or temporal data, the volume of information is just so large that a CPU cannot process it efficiently. And so those types of applications have been an impossible target to use on embedded systems or safety critical systems where GPU compute was not available. So nowadays, with the advent of Vulkan, Vulkan SC, and GPUs targeted for the embedded market that expose programmable capabilities, we can actually implement the sensor fusion operations on the GPU in a safe way that allows embedded systems and safety critical system developers to add this kind of functionality into their applications. Next slide, please. Example of a sensor fusion type operation. So hyperspectral imagery, the idea behind this is combining image data from different wavelengths in the EM spectrum using some kind of operation to allow an operator to better identify certain information on a map. So the idea here with hyperspectral imagery is that each individual element on the screen can be processed in parallel. And so this is a task that can be easily accelerated by the GPU and allows the operator to better understand the environment they're working in, and the developer can take advantage of the GPU to use high resolution images to display the information that they believe the operator needs to successfully complete their mission. Next slide, please. So now I'm going to talk about multi-application systems and what we see from a graphics driver perspective. So applications are distributed across multiple cores on a system. So what we see is that we'll have customers where they'll want to dedicate cores to a certain application, but they have a single GPU or multiple GPUs in the system that need to be shared across those applications. From our perspective, we need to support the GPU as a single resource that could be potentially accessed in true parallel by multiple cores at the same time. And so this leads to having to implement synchronization primitives from within the driver that protect this single shared resource, and leads us to the support of new graphics APIs that provide better control over how resources use the GPU. Next slide, please. So like I just mentioned, modern graphics APIs such as Vulkan allow for better control of the GPU in multi-core, multi-application systems. So first off, these APIs are designed with multi-threading or multi-core in mind, allowing the applications to build up graphics workloads or compute workloads across multiple threads or cores, and then submit them to the GPU or have the GPU consume those workloads in a parallel manner. In legacy graphics APIs such as OpenGL, you were at the mercy of the driver for how this would work for your system. There was no kind of explicit command submission and command reading in OpenGL besides APIs such as GLFinish that don't provide fine control. With more modern graphics APIs now, the application could take advantage of multiple cores on the system and control how the GPU is actually executing those graphics workloads. So to visualize this better, next slide, please. This is an example slide from a different presentation showing a typical OpenGL application where in a multi-core system, only some of the operations can be broken to other cores on the system, but there's a single core that takes the majority of the workload and spends the majority of this time building up the graphics that is sent to the GPU. Next slide, please. Whereas in a Vulkan application, you're now given the ability to break this workload across multiple cores. So each core can do a little bit of the driver workload, reducing the need for a single core doing the majority of the work available. And today, with multi-core CPUs becoming more and more common, this allows application developers to really take advantage of all the available hardware that is on their system. Next slide, please. So the last thing I wanted to talk about for multi-application systems are multi-DAL applications, or applications with, or systems with multiple applications with different certification levels, all executing on the same GPU. So this has become I would say a more common need in recent years. So as CPUs provided multi-core support, there's been a demand to have one CPU run multiple applications where each application can be a different certification level. The issue from our perspective that arises from this is that the GPU needs to be safely shared between two different applications. And what I mean by safely shared between multiple applications, I mean that one application cannot modify the memory of another application. That is, the application is protected in space, so you don't have one application going and corrupting the frame buffer graphics state of another application. The other thing is that another application cannot delay or prevent a separate application from running, that is protecting it in time. Next slide, please. So for protecting in space, on modern GPUs, they provide MMU functionality to restrict access from one graphics application to another. So this is similar to how things work on a CPU. The GPU now provides functionality like this on modern GPUs. So it's physically impossible for one graphics context to modify the state of another graphics context. Next slide, please. So for protected in time, this is a little bit more of a complex question. Only recently have GPUs started to provide preemption mechanisms to enforce scheduling on GPUs. And what I mean by recently, I mean the next generation of GPUs expected to come out, not any GPUs that are available on the market right now. But for the time being, the simplest approach is a kind of detect and remedy operation where you identify when the GPU is being overutilized and then handle that overutilization. So in this case, if an application is overutilizing the GPU, you'd want to limit the amount of work that that application can submit to the GPU so that it's physically unable to overutilize the GPU. Next slide, please. So lastly, I'm going to talk about software reuse. So in the previous presentation, there was a little bit of talk about reusing applications from a face perspective. I'm going to talk a little bit about that here. So like mentioned, there's a lot of legacy code that exists today, and lots of work has been invested into those applications, and companies do not want to waste that effort that they already invested in. So if an application can be reused, they would like to reuse it. And they would like to reuse it with minimal application changes, and they would also like to combine it with more modern systems. Next slide, please. So to reuse applications, one big component to that problem is relying on open standards. So if an application takes advantage of proprietary graphics solution that isn't open in any way, it would be difficult for a more modern system to actually support that, since a proprietary solution likely only has one or a couple vendors supporting it. With an open standard, anyone is welcome to provide a solution for that graphics API. So an open standard here, I'm going to give, from a driver developer's perspective, this would be things like OpenGL and Vulkan. These are open standards provided by the Kronos group, but ARINC A661 would be another type of standard that exists higher than the driver level that provides a more open interface to access GPU capabilities. Next slide, please. The other idea for software reuse is how to combine it with more modern applications without changing any of the legacy code. And a solution that comes from FACE for this is the idea of using compositing. So graphics APIs like OpenGL SC and Vulkan SC provide compositing extensions. So in the case of OpenGL, there's the EGL compositor. In the case with Vulkan SC, there's the KHR display extension. And these allow a legacy application to exist in a sandbox where it's only rendering to an off-screen frame buffer. And then a more modern compositing application can take the contents of that off-screen frame buffer and combine it on the screen in a more modern application. So this would give the idea of software reuse and compositing. So next slide, please. I believe that's everything from my presentation. Thank you for your time, and I'll hand it back to Paul now.
Thank you very much, Lucas. That was good. We will take back control of the screen. So our next presentation comes from Gary Gilliland, who is Technical Marketing Manager at DDCI. I'm going to try and give him control of the screen, and let's hope this works. Apologies for our technical issues this morning. So Gary is responsible for technical marketing functions, emphasizing DO-178C safety critical aspects of DOS, the DOS real-time operating system. He's got extensive experience with military and commercial avionics and real-time operating system. Gary, you have the computer.
All right, thank you, Paul.
Can you advance the slides? Yes.
Yes. Looks like I can, but very quickly. All right, my name is Gary Gilliland, and I want to talk to you a little bit about the foundational elements of an embedded system that's going to deploy all this this wonderful graphics information that's coming up. And at DDCI, we provide that foundation in a certifiable configuration, and have been doing that for many, many years. We provide an RTOS called DIOS. We provide the integrated development environment and the certification expertise to go with that. We're certified in flying and tens of thousands of aircraft, millions of flight hours, and so we have quite a solution for these types of systems to be used. So from a top level, there's several differentiations between us and a lot of the competitive RTOSs in this market. One of them is that we only focus on this market. We have one product, and that product is safety critical, DAL-A certifiable, and so we're not distracted with other markets and that do that. So we do everything with those types of requirements, the DO-178C requirements in mind. Another thing is that the operating system is designed for reuse, and I know reuse is one of those terms you hear a lot from everyone. It's been used a lot in this presentation. But when we talk about reuse, we're talking about reusing a previously certified binary that is unchanged throughout the development process. That's enabled through some of our kernel technology that's been able to link and load, which means that basically your core AVI driver that was developed and certified on one system can be used, in a similar architecture over and over again without having to go through any of the certification process. It's a huge time and risk cost savings. Along with that, there's a lot of other technology that I'll talk about that is been patented over the last 20, 30 years. So key there is that we're focused on safety critical. Oops. So like I said, our background is this mission safety critical environment. The operating system is designed from the ground up to be certifiable and support multiple DAL levels in an integrated modular avionics way. First certified back in '98. We are, our next planned certification is later this year, and we plan on, and we have more lined up in the current pipeline for that in a multi-core environment. So one of the things, people ask a lot of times is, have you been here before? And I'd just like to show this as a certification baselines that we've created, show the pedigree of this product. We've had various different baselines over the years. The product originated actually at Honeywell back in '98, first certified there. In 2008 was taken over by DDCI and has been managed by DDCI from then on. Just so happens that we also acquired all the engineering, the people, the products, the plans, procedures that developed that OS. So all of that is the same and unchanged over the years. So it's kind of a single ongoing line of development. Worked with a lot of auditors in the industry, and we encourage you to talk to these auditors to get an understanding of how it is to work with DIOS and what our expertise and technology is. These, if you notice, these are all FAA, EASA commercial certifications, and while we do run a military aircraft as well, these are the highest level of certifications that you get in the industry. So from an architecture standpoint, DIOS is a microkernel architecture. If we look kind of in the middle of the picture there, the DIOS kernel is a component. For say an ARM platform, that kernel is the same kernel on a on a low-end ARM, you know, say, you know, ARM A9, ARM A15, ARM 53, 72, that same kernel is used throughout. The differences in ARM architectures or hardware platforms is taken care of in this, what is seen there as the PAL, which would be a platform abstraction layer, which happens to be a separate component. So that component defines all the natural interfaces for the system, the hardware, how many cores are there, where the RAM, flash, timers are, all that kind of stuff. And then the registry defines the characteristics of the system. So how many partitions are there, what partitions have access to what hardware, and that kind of thing. The registry is the information the kernel uses to basically understand what's going on in the system, what you've designed, and how to control all the access to any of those resources. So that's key. Up above that, you can see that in our case, most of the drivers are typically in user mode. So those, there's a couple of reasons for that. One, it's easier. It makes them, you know, just like any other application. Another one is you can design them to the level or the DAO level that's required for that particular interface. If you include all your drivers in the kernel, then those drivers have to be designed to the same level as the kernel. Therefore, it costs more, there's more time, there's more energy, more risk, and that kind of thing. So we feel like this is a better model. There are ways to move those graphics drivers down if you need, you know, higher interrupt control or something like that. They still don't link with the kernel, but they operate in the supervisor address space. So from a reuse standpoint, I'm going to reemphasize this idea of binary modularity. It's the idea that not only can you reuse an application and a particular kernel from a certified system on a new system, but you can also reuse all the artifacts associated with that. So we all know writing software is actually the simpler part of doing a certified system. The actual, all the data, all the tests, all the requirements, all the stuff that proves that your software does what it's supposed to and nothing else, that takes more man hours than, you know, the actual source code itself. So being able to also reuse all those artifacts is very important. And the way that is done with DIOS is this technology I said in the kernel with it's basically a linker loader. DIOS is a virtual address machine. The kernel will come up, decide, you know, put your application in a virtual address space, add the library, and enable that application to run. So it's something that we use in the kernel, and the way the kernels work, it also enables and eases our job, makes it easy for us to certify from version to version, but it also enables you to develop your application with that particular component type of a library. And I think you can see that from the previous presentations as well. It's all component based. So you put these components together to build the HMI, put the library components of the driver together to interface with that HMI, put all those things together, and then you can reuse these pieces across various different platforms all along. So kind of how it would look, kind of a notional example here is each one of these colored boxes would be a particular component, maybe a user interface component, maybe an OpenGL library, a display library. The ones on the bottom are the ones provided by the kernel, by DIOS, math, ANT, IOI, they'll share. But each one of these would be an individual component that have its individual connections and have its integrity key that proves that that particular binary didn't change, and the artifacts associated with that didn't change. So when you think about doing all this in a multi-core environment, like it's been talked about before, you have to follow all the DL178C capabilities or practices, processes. But in addition to that, the certifying authorities have also laid out guidance in something called CAS 32A, which is extra information that you have to follow to prove that you're going to be safe in your multi-core system. So in order to address the CAS32's concerns, which are mostly around the idea of interference and controlling interference, we've implemented something that basically a three-phased approach to that. One is called safe scheduling. The second one is a concept of memory pooling and cache partitioning. And then the third is this safety net idea that's mentioned in CAS32. So we'll talk about that a little more in the next few slides. So from a safe scheduling standpoint, the idea here is that you have to prove that the applications you decide to run at the same time across from each other or execute concurrently on different cores don't cause bad interference between each other. So basically, you need to define. I always look at this as a kind of a three things you need to do. First, you need to figure out what applications, when they run together at the same time, in parallel, give you higher performance. And then look at what applications maybe use the same resources, the same I/O, and you don't want to run those at the same time. You want to separate those out in time. And then some that don't matter. Maybe they're just memory intensive applications that don't affect anybody else. So you need to look at your applications and then define these windows of time across your major frame, and so that they can work like that. But basically, you want to make sure you define what can and cannot execute concurrently, so that you can meet your worst case execution times and bound and control the contention that could arise from the way the hardware works and the way memory and memory buses and that kind of stuff. So within that windowing system, you can run various different scheduling algorithms. So rate monotonic, which is the DOS native priority, which is a priority preemptive real-time execution with time budgets on threads. You can also run an ARINC 653 partition. That's the industry standard for API. You can also run a combination of the two, as well as you can run a POSIX preemptive scheduler as well, such as our POSIX scheduler meets the safety-based profile of the FACE technical standard. So when you're looking at interference patterns in multi-core, we've been looking at the architecture and the technology of this for 10 plus years, and it's determined that cache is really the greatest performance factor. It causes the most variability in execution time, and you really have to do something about that in order to minimize that and bound your worst case execution time. A little example here is just, even on a single core system, if you have two applications that are sharing a cache and, just reading one variable, they could, because you have no real control about where that gets stored in memory, they could have to do a flush and refill every time they access, one single variable. It's very common. It's actually this reason that we decided to implement our cache partitioning scheme in our single core kernel back in 2017 and have that certified back then, because we found there's so much improvement to performance by doing that. When you take this to multi-core, you really have a similar problem. You have core 1 doing its thing, just like I showed, and now you have core 2, core 3, core 4, how many ever cores you have, that all could be fighting over cache amongst themselves, or they could all be fighting over the same cache. So you have to figure out how to manage that. There are solutions or some capabilities out there in hardware to do a hardware partition of cache, and that alleviates your shared cache issues, at least for a particular core, but that still limits you to being able to only run one application per core to eliminate all this cache thrashing. So the idea is you need to somehow partition that shared cache. And so The way we do it is the idea of being able to partition it on a per application basis. And we do it in a very portable way. It doesn't require any particular hardware capability. And like I said, it's been previously certified, and it is a patented mechanism. So from this picture, it looks like you can see that you got multiple cores with multiple applications. And if you think about, or if you understand how cache works by memory addresses. So in a virtual address machine, you get to define, or we get to define, which pages of memory are used for each application. And if we define it in such a way, we can actually make sure that a particular application gets into a certain area of cache, a certain number of cache lines, and only uses those cache lines. The second one only uses those cache lines. So in that way, there's an ability to basically partition that shared cache so that it's individual for each application that runs. So when you get a context switch, you come back, the cache is undisturbed, the application just keeps running. An added benefit is you can actually, because it is memory pools that you are defining, you can actually define what memory certain applications go in and how they operate as well. So if you have a lower end process with on-chip fast RAM and off-chip slow RAM, you can put your safety critical, fast critical applications in there. So this is just kind of an experiment that was done by one of our customers. Shows that if you use L2, the shared cache with no cache partitioning, then your variation in execution over 1600 frames, it varies. That gray band is showing that variation, and it's from approximately 30 microseconds to 100 microseconds. If you turn L2 off, which is recommended by some of our competitors in this space, you certainly reduce your worst case execution variability time. So that red band represents that, and yeah, it doesn't vary as much, but the performance is significantly slower. Your best case performance now is up a little bit above 60 microseconds. And then the kind of lime green band down there at the bottom is implementing cache partitioning and running that away, and you see that it actually lowers the variability, but it also preserves the performance. So you're getting very high performance, and your worst case execution time is not over 40, which gives you 60 microseconds in this scenario for more time to do other things in your system. So that's the key. This cache partitioning is really like the key thing, and it dramatically reduces worst case execution time on these systems. Oops. So the other thing is this idea of safety nets, and with DO 178, following that process, you go through, you define your requirements, your tests, you test your requirements, and you prove all through the way that your software does exactly what you says it's supposed to do and nothing more. In Task 32A, it has basically the same kind of a process, but at the end, it also says, what if it doesn't work? What is your safety net for that? So you have to have a way that even through all your verification, you verify what it is, you need a backup plan. So in this case, there are performance counters in most of the common hardware that's out there today. Most of the CPUs have some way to either performance counter, monitor. There's different names depending on the architecture, but they have a built-in hardware capability to count processor level events, and it gives you the ability to set thresholds on those events and interrupt you if one of those thresholds is exceeded. So basically for DOS, we have the capability to set those up, recognize that an event occurred, and then when that event occurs, know what is the offending process that's causing that particular event, process, partition, whatever, and be able to then allow your health monitor to decide what to do about that. If you want to hold that guy off for a few cycles, if you want to restart that particular partition, or whatever you as a system integrator think is the proper response for that. So it's basically giving you a way to provide that safety net. One of the key things to remember about this is these hardware monitors are the least tested part of the CPU. So you have to look at the errata, be very diligent at looking at that for these particular hardware architectures, because there's things that you can do and can't do, and that's where most of the errata is in the CPU. So just be careful. So from a summary standpoint, very high pedigree record, unmatched record of deployments, lots of features for developing these systems, very high performance, low overhead, and extremely quick boot times, and then all the tools to provide the capability to get you through verification and deployment. The kernel actually measures the worst case execution time of all threads of the system and tracks that and gives you that information back to the tool. Plus, we also integrate with other tools like Rapida that give you worst case execution time and demonic adversaries, as they call them, to test your system and guarantee what the worst case execution time is going to be. So I want to thank you and pass control back to Paul.
Thanks very much, Gary. That was very interesting. I appreciate that. Okay, I think I have it. So I do apologize to everybody that we've gone over the time that we aimed for. I see that there's still many people online, so I assume that this has been of interest to you. Okay, all right. Well, at that point, I think I'm going to say thank you very much to the presenters for their presentations, all of which I found interesting. And I'd like to thank everybody who's attended and all the people who are still online now, even though we have gone way over our original time plan. I apologize for that, but thank you for staying on. As I said at the beginning, when you leave the meeting, there will be a short survey. We would appreciate if you would complete it. Thanks very much and goodbye.